I had an email from folks who are homesick, wanted to know, how do I watch the class while it's going on? You go to YouTube and it should be streaming. There's a slight delay. I've deactivated comments so that I don't get little pop-ups while I'm talking, but otherwise you should be able to participate from anywhere in the world that has the interweb. So the Christmas creep is upon us. Normally, I open the show with, "Hello friends, it's good to see you." That's Michael, the music teacher at my son's school. And I asked him yesterday, because Tuesday is music day, "Oh, did Michael sing Hello Friends?" No, he sang Jingle Bells. I'm like, okay, so then we had to go find YouTube videos of Jingle Bells to watch on the way home. And then when we were at Kohl's, it was already set up for Christmas in the back too. So what is going on with this world? I can't understand. I refuse to sing Jingle Bells, so I'm going to stick with Hello Friends, it's good to see you. Does that sound fair? Yes, I think so. So hello friends, we had a quiz. How did that go? Let's take a vote. How did that go? It was, you have three choices. Easier than I expected, about as hard as I expected, or way harder than I expected. Close your eyes. This will be anonymous. Okay, take votes for easier than I expected, about as hard as I expected, way harder than I expected. Okay, well that means good. You all have good, reasonable expectations then. So let's go over the answers. They should be in front of you, but just in case there's any points to clarify. So what is a logit? Say it with me. The log of the odds of the probability of a 1. Yes, or you could say log odds would be a little bit shorter, but that doesn't convey what it actually means. A logit is a link function. That is what you refer to a logit as. So when you do things, when you write result sections, you would say that you specified a logit link. That's how you would explain it. Now, why is a logit? What's the point? What did you guys tell me? Put a creepy screen down here. Why is a logit? What do you think, Heather? Yes, the logit is a link function, which means that it transforms the outcome to be predicted from something that is bounded to something that is unbounded, or continuous, yes. That way, we can use a typical linear model that makes predictions that keep going and going and going, but when you back translate it into probability, the probabilities are bounded between 0 and 1 like they're supposed to be. So what is the technical name for back translate, by the way? I-link, which is inverse link, yes. So when I say unlogit or back translate, that is actually inverse link. So you'll see the technical terms in books, and I want to make sure that we know how to map those on. We also started talking about the IRT models, 1 parameter, 2 parameter, 3 parameter, 4. And so the next 2 questions were asking about the meaning of those. So what did I do first, B or A? I did B, because that's the first one. So what is a B parameter in a 1 parameter IRT model, for instance? Synonyms for it. Difficulty, there's one. Another one that starts with L that you would hear. Location, yes. So the definition of a B then, mathematically, it's the point on the latent trait at which your probability of a correct response is 50-50. So it locates the item on the same continuum as the trait for people. So that definition of B is the same in both the 1 parameter model, in which all items are assumed to be equally discriminating, where we don't have individual A's, and in the 2 parameter model, where each item does have an individual A. So what is A then? Discrimination. Give me some more synonyms. Slope. Yep. It is going to become a factor loading, but not yet. Maybe by the end of today. But they literally will be the same number. The definition of A mathematically is it is the slope at the point of difficulty. So when you see the item response curve, the item characteristic curve, let me get some pictures out rather than waving my hands at you. The point of inflection on the curve where the slope is the steepest, that is the slope of A. So it's the slope of the line that's tangent to the curve at that point. So let me find these pictures. Those are C parameters, this one. So in the model, where the item is centered, essentially, the point at which the curve crosses from heading up to heading down, so it's accelerating and then it translates over into decelerating, that point is B. And then the slope of the line at that point is A. And then, what else we got? So how are we doing so far? Good. Okay, what kind of conditional distribution do we use for binary answers, and what are its parameters? Starts with a B. Bernoulli, yes. You could also probably say binomial, because Bernoulli is a special case of binomial when you only have one trial. And how many parameters does Bernoulli have? 1. That's what I want you to remember. It only has a mean. The mean is the proportion of people who got a 1. The variance is determined by the mean. It's the proportion of people who got a 1 times the proportion of people who got a 0. So that's why there are no residual variances for the items in these models. It's not that they're perfect. It's that the variance is determined by the mean conditionally, so that it changes as a function of what the predicted mean is. It shrinks as you get closer to 0 and 1. And that's the idea of conditional distribution. When you see that word, that means after something. So it's the idea that after controlling for theta, the answers have a Bernoulli distribution. So when you say conditional, that's what that means. And then last but not least, why can't we use a normal instead? Why can't we do CFA on binary responses? Three problems. Go for it. Yeah, so the normal distribution has two problems. Obviously, answers that are binary can't be normal in any way, shape, or form, and they can't have constant variance. But then other than that, the logit part, so it's the use of the logit that solves the other problem, the idea that the line needs to shut off. So the logit solves the linearity problem. The switching of the conditional response distribution to Bernoulli solves the variance problem. So functionally speaking, we are going to do CFA on binary answers. We're just going to do it on the logit of the binary answers and pick a different response distribution. Conceptually, it's still a confirmatory factor model. Just at this point in time, it does not look like one yet. All right. So questions before we move into new stuff? Anything you want to hear again or talk about? I hear the mouse scrolling, and it actually sounds like crickets chirping. No, we're good? Okay, more vocabulary then. We did some more vocabulary stuff. Let's see here. 3 and 4 parameter model adds C and D, lower asymptote. If your prediction stays above a probability of 0 because of some other reason for that item, or will not get all the way up to 1. You can have a lower or upper asymptote. We're not going to do any of those. What we used to call identification is called anchoring, but it's the same too. Theta needs a mean of 0 and a variance of 1, or else it needs one of its difficulties fixed to 0 and its slopes fixed to 1. We're almost always going to do it the first way, though, because that makes it easier to understand what theta means. Then we get into reliability, and this is where we left off yesterday. Would this be a good place to start? Just pretend I never said any of this? Yeah? Okay. You all look so serious today. What's up? Is it because I won't sing Jingle Bells? Because you know I would if it made you feel better. I really hate Christmas music, by the way. I really, really do. I'm one of those people, right, that every radio station starts dying off in November, and I get grumpier and grumpier until December 26th when they all come back. But I digress. So reliability in IRT is not going to be one number. That's the big picture here. Because these slopes relating the trait to the item are nonlinear, that means items that are good aren't good the whole way through. They're only good in the spot where their B is. They're specific. So reliability is going to be a function of how many items you have at each point on the trait and how discriminating they are. So this is a different concept relative to what we had in CFA. So let me explain what this would look like in the context of a CFA model, which is linear. So I had this in one of the slides and probably never even said it out loud. You can compute something called item information in CFA. It's the unstandardized loading squared divided by the error variance. The sum of information across items is what's known as test information. And in CFA, test information is going to be flat across theta. It is a single number that is supposed to hold equally across the trait. The reason that I never bothered to mention this is because if you want to know how informative an item is, a much more ready statistic for that is already on your output. It's the standardized loading. So you can look at the standardized loading and say, well, that's a correlation with the trait of whatever, and that number readily means something. Item information is scale specific. So you don't know if it's good or bad because it depends on the total amount of variance that an item has. So this is a new concept that shows up in IRT. So here's what the CFA model would look like. It's linear. So this is the big thing. We are saying that a 1 unit change in theta is related to the same unit change in my predicted response. And in this case, the red line has a slope of 0.8, and the blue line has a slope of 1.2. I take those unstandardized loading slopes, square them, divide by the error variance for each of these items, and these are my item information functions. So item 6, the red one, has an information of 0.4. Item 1 has an information of almost 1. I can convert total information, test information, to reliability with this handy-dandy formula. And I almost always do this when I talk about the results of an IRT model because no one knows what information is in its own metric, but everyone knows what reliability is. So information divided by information plus 1 gets you to a conventional metric of reliability that ranges from 0 to 1. So in CFA, if I were to plot the amount of information in an item across theta, that would be silly because it's flat. If the blue item here is better than the red item, it's better for everybody equally. It has a stronger slope, and the slope operates equally all the way across theta. That is not the case over here in IRT world. So if we plot the information that is contained in these pink and purple items right here across theta, it's a different number. So there's a formula in the Embretson and Rees text by which you can compute information. M+ will do this for you. I'm guessing R will do this for you, or any other IRT package. And so what this is a plot of the amount of information available at specific values of theta. So you can plug in a theta and get the information back out of the formula. And so I want you to notice two things here about the pinky purple lines. In addition to the fact that they're not flat, they are centered at a theta of 0. They are both highest at a theta of 0. That's because that's what their B value is. So information is maximal right at the value of their location, of their difficulty. Second, pink is higher than purple because pink has a steeper A value, a steeper slope. So it contains more information at the same point. So content aside, if I were trying to create a short form and I had to choose between these two items, which one do I want, pink or purple? Pink. but you can't pick a short form without paying attention to where these things are centered in the first place. Because you want items that have maximal information over here on the right so that you can measure people with high trait values well, and you want items that have maximal information over here on the left too so you can measure people with low trait values well. So the summary then of reliability for your test can't be a single number. It's a function. It's called a test information function. So here is an example then that has more items. So we made this plot in Excel. Some of the items have slopes of 0.5 and some of them have slopes of 1, and then I spread them out so that these two have a difficulty of -1, these two 0, 1, and 2. So if I took those item characteristic curves, given those item parameters of A and B, and I plotted them as information instead, they look like this. So this helps illustrate the point that I was trying to make a little better. I want 4 good items out of this. I picked the tall ones. However, what if the goal of my test was to find, with great precision, really, really, really high people? Then which 4 do I want? Yeah, all the ones over here, even the ones that aren't as tall, because they're still going to help. If once you're past some point, I don't care how low you are, I don't need any items down there. Vice versa, if I really want to measure low people well, I pick the low items. So you can see, based on your test information function that is literally the sum of all of these curves, where the holes in your test are and where you might need to add more items or add more response options. So we'll see lots of plots here to try and illustrate that point in this unit and the next unit. So then this is a picture of what a test information function might look like. That's the blue line there. The inverse of information is standard error. So in your output, you can ask it to predict each person's most likely trait score, and you'll get a standard error with it. 1 over the square root of test information is that standard error. So the more information, the more precision you have with which to say how high or how low somebody is. So here's a slide that I am using to make fun of myself. So do you remember when I told you guys the other day that you guys already know way more than I did when I graduated, and you didn't believe me? So this is a slide from my job talk. Okay, so this is after 2.5 years of postdoc, 4.5 years of graduate school and whatnot, because I thought I was going to advertise how well I knew IRT. This is the test information function from a measure that I developed for my dissertation. I believe this was published in Educational and Psychological Measurement, by the way. What does the y-axis indicate? Test information. Now, the point that I wanted to make when I put this picture in my slide was that the goal of my test was to measure people who had deficits, and therefore that this was higher on this side was actually a good thing. But how high is it? What does an information of 2 correspond to? Which is the top of the y-axis, by the way. Information over information plus 1 is reliability. What's 2 divided by 3? 0.66 repeating, right? Would anyone call that acceptable reliability? Nope. So this is my illustration here that I didn't even really realize what information meant, even when I made a picture of it and put it in my job talk and put it in a paper. What it would be far more helpful is to take this y-axis and translate it into reliability so that it goes from 0 to 1, and then people will know what you're describing. And so when I describe the reliability of a test, what I typically say is this trait had decent reliability from, -2 standard deviations up to 1 standard deviation or something like that. You can summarize the range of the trait over which reliability meets some cutoff, like 0.8 or 0.9 or whatever you're doing. That's what I would do. Whenever you see any kind of single number instead, it either came from one of two ways. Either they did alpha, which is just silly, or they did some kind of marginalized reliability where they took this curve and they computed basically a weighted average, weighted by how many people were in each of these theta bins. So you can weight across and end up with one number if you do it that way, but to me that's also silly because that obscures all the differences in information across the function. So in order for you to have a really good single number of reliability, most of the people need to be in the range where your information is highest, with relatively few people out here. So this is more of a theoretical result than an actual one in that sense. So this is a more egregious example of what you might want a test information function to look like if what you're trying to do is classify people. Like decide if someone else needs more treatment or needs to get remediation or needs to go to the gifted program or what have you. You want to maximize information around the point where you want to make your cut. And that's what people would do in an IRT framework. So this happens in the context of end-of-grade testing, for instance. Some of you are from ed, right? Right? What do you get at the end of grade testing? You get some sort of number of the kids who are meeting proficiency standards, right? They spend 3 days or 3 weeks testing to get a continuous trait, to sit in a room and meet and decide where to cut it up to define proficiency. Well, if all you want to know is proficient or not, that turns out to be way easier to do if you don't try to estimate an entire trait and then just cut it up. And so those are the models we talked about at the beginning of this semester, diagnostic classification models, also known as cognitive diagnosis. Those models directly have a trait that is cut up in them. They say that the analog of theta is a binary latent variable. And then what you get in your output is the probability that each person is a 1 on that binary variable. So if that's what you want to do not use IRT. Go straight to these because the models are designed for classification. So summarizing then, how much better? More items is always better. In classical test theory, it doesn't matter which items they are. In CFA, if an item is better, you're assuming it's better for everyone because a stronger loading is a stronger loading all the way across the trait. But here, you have to ask yourself, how much better and for whom? Location matters. How are we doing? So how much better? This is a picture I stole from Susan's book, highlighting the benefits of adaptive testing. So this idea that once you have a pre-calibrated set of items, meaning you have items that you gave to a big enough sample to where you can get A and B values that you trust with decent levels of precision, then you can give people the same test and just score it super quick. You don't have to re-estimate all the A's and B's. And that allows you then to do computer adaptive testing. So in this case, if you have a fixed test, the standard error for your trait, which is the inverse of information, would likely have this sort of U shape, where if most of your items are mid-range difficulty, that's where your standard error of measurement is going to be smallest. You're not going to get a good handle on the super high people or super low people because you don't have enough items that target them specifically. Whereas if you can give an adaptive test, you don't waste people's time with items that are too high or too low, then the same number of items can be used to get really good measurement all across the trait. So you can use this calibration idea and linking in your favor so that you can change the items that you give over time or across samples and do so deliberately to make sure that you maintain sensitive measurement. So for instance, if I have 6 items at time 1, I may drop off some of the easy ones and pick up some harder ones at time 2, drop off the easier ones, pick up some even harder ones at time 3. The reason that this design works is because I have a set of common items. And if I am willing to believe that those items function the same way across time, that their A and B properties are the same no matter if you give them at time 1, time 2, or time 3, then you don't have to give all of the items all the time. The linking, though, is the key. If I gave items 1, 2, and 3 at time 1, and then items 4, 5, and 6 at time 2, I am screwed. Because you can't tell if any discrepancies would be because of the person changing or changing differently. You don't have any overlap. So this feature can be used to calibrate tests. It can also be used to combine measures. So who was talking to me about that? I think it was Ryan, but he's not here today. Too bad, Ryan. I hope you're listening. I was going to give your example. He has 2 measures of affect, the PANAS and some other thing, and he wasn't sure which one he wanted to do for his project. The PANAS has been beaten to death, and the other thing has been beaten less to death, and so we picked the other thing. But they're both scales designed to measure the same thing. So here's another instance of this type of thing. So there are measures of physical functioning. The SF36, I can't remember what that stands for. Adrian, do you know? No? Okay, you've heard of it before? No? Okay, well maybe I'm just dating myself then. But there are items that are meant to quantify the physical functioning of very active, able people, like runs marathons, can rake their yard, that kind of thing. And then there is activities of daily living that are meant to quantify the activeness of people who are more sedentary or potentially who have disabilities. And so if you want to do some kind of literature review or meta-analysis about what things predict functioning, or if you want to design a study and you're not sure which measure you should use, right? Maybe you have a sample of people that's right in the middle. They're not likely to have significant disability, but they're also not likely to be marathon runners. Wouldn't it be ideal, if you only have time to give one measure, to get some items out of one and some items out of the other, kind of like a happy medium? If you had a sample of people who took both at the same time, you could do a calibration and then just pick from that subset which items are going to be most useful to you. So a lot of times people will hedge their bets in terms of what measures they give because they're not sure who they're going to get, and they'll give multiple measures. Rather than having the measures fight against each other, you can make them work together in deliberate ways. So I've seen this on other measures of like alcohol consumption or sleep deprivation. They might pick 2 or 3 common measures, and then you can link them together onto one trait. So this was a workshop I attended, and I stole this picture from it because I really liked it. The idea that you can have a longer, more continuous ruler if you make the measures work together than if you only give one or the other. I want to do the example before I go into this stuff because this is more sort of theoretical stuff. Is that okay? You want to see how this looks like in MCode? Remember what I promised you last time? What did I promise? How? One more line. It's a beautiful thing. So let's look at the example. Because I think pictures and real data make this easier to wrap your head around how you would go about doing this. The good news is that you do get to go about doing this in homework 5. So homework 3 is out right now. You get to use your own data and run a CFA on it. For homework 5, I'm going to want you to do the exact same thing. Run an IRT or an IFA on it. So this, let me get my spreadsheet out that goes with it. Homework 4 is another canned data one, as is 6. But we won't worry about that yet. There. As always, I have a spreadsheet that shows calculations for things, as well as how I made pictures. So I'll get that out in case I need to show it. So these are real data. This is a sample of older adults, 635, I believe, and these are activities of daily living. 7 items that had 2 versions of a response. Either they need help or they don't need help. So one is don't need help, meaning they have a higher ability to live independently. And so for this example, we're focusing just on that. There's also a categorical version that we'll look at when we get to polytomous models next week or so. Yeah, you should. It should be on, I posted it for the last class. Let me find it. Example 5. Sure, yeah. So that one, there should be this document, output files, and then the spreadsheet. No problem. Yeah, we didn't get there last time. I should have just moved it down to today. I'll do that after class. I try to keep the handouts and the videos like on the same page to whatever extent I can. But so these are the 7 items. What do you notice about all of these proportions? These are the means for the items. How many people can do this without help? They're all above 50%. So the easiest item looks like it's number 7 using the phone. 94% of the sample can do that. The hardest item looks like it's going to be shopping, which in this sample means like walking to the store. This is data collected in Sweden where it's not as much with the cars there. So this tells me right away that I'm going to see some kind of floor effect without doing any analyses whatsoever. These people are more able than the items are difficult. So here is the syntax for 2 different models. The 2PL is on the left. The 1PL is on the right. The difference between these, both of them have a separate B parameter for each item. Yeah, we'll just look at that part of the output. And only on the left do they have separate A parameters. So find where in the code that distinction is made. We'll play Where's Waldo. Well, Linkus Logit is on both sides. Remember one of the synonyms for slope, loading. So where am I asking about loadings? Yeah, first line under model. I have the word loading here. When you have only one term, that means you're saying everything in the line has to be the same. So in this case, I am estimating separate loadings, which is going to be our discriminations, from 1 to 7. That's all going to be one number, whereas on the other side, there's no constraint. So this, if I wanted to have a label on here, I'm not doing any math, so I don't need it, but if I wanted to, I would do something like this, loading 1 to loading 7. That would make it explicit that there are 7 of them as opposed to 1. So I told you before that the models that we're going to look at are actually factor models. We haven't talked about what these things mean yet, but they are the analogs to what difficulty values are. Fortunately, in M+ for binary items, M+ spits out the A's and the B's in addition to this version of the model. So we'll look at the A's and B's first, since that's what we've been talking about. And then last but not least, here is my model identification. IADL is the name of my factor, my trait, my theta. In brackets, @0 means that its mean is being fixed to 0 for identification, and listing it with @1 means its variance is being fixed to 0. So that's it. The new different line of code that you haven't seen before is right here. Categorical R. This is beautiful. All you have to do is say that, and M+ will read your data, figure out how many categories you have, and figure out what all needs to be in the model as a consequence. It's beautiful. Yes, yeah, I like that look, Lucas. He's like, really? Damn! It's beautiful. So we're going to talk more about this later, but I want to point out that this is all we get for fit. The model on the left is the 2PL. The model on the right is the 1PL. So we get HO. What's normally after HO? H1. And then we get information criteria. And then these are new things, chi-squares. And then that's it. What are we missing? What other fit things are you used to looking for? RMSEA, CFI, TLI, they're gone. Did I screw up? No, they're gone. Here's the thing about categorical data. There is no single covariance matrix to come back to when you're using full information maximum likelihood. Categorical data are not described by only two things, mean and a variance. What is the analog of covariance in categorical data actually goes past that in terms of moments. So what M+ is trying to do here under the hood is maximize the likelihood of a contingency table for every possible combination of item response. So it's 2 to the 7th possible, if you do like a 7-way chi-square thing with your arms, that's what I'm trying to do here, that's how many cells are in it. 2 to the 7. It works out to be 100, I figured this out here, it's on here, 128. So in the 2PL, there are 128 possible cells, 2 to the 7th. That's the analog of total degrees of freedom here. We don't have item means, variances, and covariances anymore. That's gone. What we have is a 2 by 2 by 2 by 2 by 2 by 2 by 2 table. That's the data going in. The things coming out are the parameters. And in this case, 7 loadings, 7 discriminations, and 7 other things that are going to become b-values. The difference then in the 1PL is that there's only 1 loading instead of 7. And so that's where those numbers come from in terms of these chi-squares. The 113 degrees of freedom here is the number of other things I could add to the model to try to recreate that 2 to the 7th contingency table. These chi-square values, though, are actually invalid. Number one, the easy reason is that on the M+ documentation, it is recommended that if they disagree, that's a sign that they're not valid. So the fact that one is non-significant while the other is wildly significant might cause alarm. But practically speaking, do you remember what happens with chi-square values? Remember chi-square tests like from a million years ago? There was a rule about when you shouldn't pay attention to the chi-square test. Something to do with the number 5. Remember? If you have expected cell counts below 5, it's not valid. So that means we would need at least 5 people per cell in my 2 to the 7th contingency table. And there's only 7 items here. So no, these chi-square values are basically useless. You can disregard them. Only when you have a whole lot of people and not very many items would they be valid statistics. So fit in IRT is super hard. You will not see any attention paid to fit often when people report their models because these absolute fit statistics are basically useless. There are other ones that have been invented, they're not an M+. So if you go back to your homework 1, several of you reported IRT models. Go look through those again and see what they said about fit. They didn't. So I may have noted that when I saw that, but this is the reason why. Absolute fit is super hard. We can do aspects of bivariate fit, but so long as you're using the world of full information maximum likelihood, this is all you get. We'll talk about an analog to that. What we can still do, though, is our friend -2 log likelihood difference. So the model on the left has 7 slopes for 7 items. The model on the right has 1 slope for 7 items. So they differ by 6 parameters. We can take -2 times the difference in our HO log likelihood and find out whether or not the model on the right fits worse. I did that for you down here. The difference is about 20 on 6 degrees of freedom. So yes, constraining the slopes to be the same hurt fit, so we don't want to do that. So relative model fit is, relatively speaking, how much better is one model than another as a function of what you added or took away. Absolute model fit is how good is your model relative to perfect model. There is no such thing as perfect model anymore, and that's why there's no H1. So let's look at just part of the output here. The second column, this is from the 2PL model, since 1PL didn't fit very well. So this is IRT text. This text right here, this is from EPSY. It says, this is the IRT parameterization in a two-parameter logistic metric where the logit is discrimination times theta minus difficulty. Got all that? Let me make it easier for you. Come back. Let me find an A parameter. This. That is what they just said. They're telling you how they parameterize their model, since there's 18 different ways that you can do it for this. In previous versions of M+, they also stuck a 1.7 in here, and that's gone. So we don't have to worry about that, but that is the difference between logit and probit. So these right here, this IADL by, these are item discriminations. So this is the A parameter for each item, the slope at its point of difficulty. These numbers are really big. Have you ever seen a slope of 7 before? They're in logits. Keep that in mind. Down here are the item difficulties. These are the B values, the locations. This is the amount of trait that you need to have a 50-50 shot at being able to do each of these tasks. Now, what do you notice about these values? Do they have anything in common? They're all negative. So is this test easy or hard? Easy, because it's theta minus difficulty in the equation, these really are difficulties. So it takes less than average on this trait to have a 50-50 shot at each of these items. Which one of these is easiest? Smallest? Yeah, the number 7. That corresponds to what we saw in the data earlier. Answering the phone, which one of these is hardest? Looks like the first one. Is that going shopping, I think, or is that cooking? It's what? Housework. Oh, yeah. So in terms of reliability, what's going to happen without me even looking at that? Am I going to be able to measure able people very well? Nope. I don't have any items that are targeted to people above average. None. So here's a picture then of what my test information function looks like from those items. Here's the item characteristic curves. They're very steep. That's very good. That means they're discriminating. But they're all discriminating in about the same range here, from about -2 standard deviations up to not quite 0. So that creates a test information function that looks like this. So I have 4 down here marked on the y-axis because 4 corresponds to reliability of 0.8. Information over information plus 1 is the formula that goes back and forth. Here is this same picture converted into reliability as a function of the trait. So there is not one number that I can give that says the reliability coefficient for my test is this. Is this a good test? Is this useful? What your answer should be? It depends, right? So if you are, let's go minus 1.8 standard deviations up to about average, this is a pretty good test. So if my goal were to measure folks with the intent of figuring out who needs extra help getting through their daily life, the people on the low end are probably those that need extra help, and I'm doing good. If I'm trying to figure out which of these older adults I want to put in my marathon training program, I have literally no information with which to do so. Reliability tanks right after 0 because I have no items out here. How would I fix it? More items, right? But any more items? More good items? More good high items. That's what I need to fix this. I need more things that are harder, that these people who are all at the top, who said, yes, I can do everything, that they could start to spread themselves out and some could say no to. Consequently, because of this reliability function, this information function, that causes this theta distribution. This is a histogram of the most likely guesses for each person's theta in my sample. This is what F-scores makes you. I have a ginormous ceiling effect. Even though theta is supposed to be normal, and you can ask for it to draw a normal curve over it just to make that point, nope, can't be. That pile at the end is the people who said yes to everything. I have no information with which to sort them out. Here are the summary statistics for those factor scores. The mean is right near 0 where it's supposed to be. However, this number right here, that's the variance of the factor scores. That number is 0.7. What was it supposed to be according to the model? 1. Ruh-roh. This is why we don't want factor scores if we can help it. This problem is what's known as shrinkage. Extreme values are reeled in. There's always going to be more variance in the model than in some kind of observed variable representation of the model. Okay. Here's a plot that shows item difficulty for each of my 7 items. So you can see, relatively speaking, how much more difficult some are than others. Keep in mind the y-axis here now is difficulty. That's the amount of the trait that you need to have a 50-50 shot at doing each item. So I like difficulties because I feel like these are really intuitive relative to the other version that is the default on your M+ output. How are we doing? A's and B's? Slopes and locations? Now, let's see. What do I want to do? I think, do I want to show you how this is actually the same thing as factor analysis? Yeah, I do. I'm going to skip these 2 slides because there's a reading about this. But the point is that information comes from where your items are, and if you don't have enough items in a certain place, information will be low at that place, and that's what you would want to know to fix. So let's go to this one here. This is slide 54. So when you use the combination of talking about your model in terms of A's, B's, C's, and D's, and you use full information maximum likelihood where the model is trying to capture the full possible contingency table of response patterns, that, my friends, is IRT. That set of terminology and estimation together is collectively known as IRT. If you are writing for an education journal, you did IRT. If you are writing for a psychology journal or medicine, you did IRT too. Maybe sociology, you did IRT, but things that are more like on the social sciences towards like psychology, you want to say you did factor analysis. So here's how you get from one to the other. So linear regression, CFA. Then we have this thing, which is logistic regression. So we drop the E, and somehow that is supposed to be the same thing as this. Here's how you get back and forth. This thing always, no, come back. For whatever reason, this one slide always moves over this little ogive thing. It drives me nuts. There, get over. Okay, here we go. We can write this logistic regression or probit regression model as a factor analysis model, just like you're used to, where the slope is the same, but what used to be called an intercept is now this thing right here. -1 times that thing is called a threshold. That tau thing. So what M+ estimates directly? This is the IFA version of the model, item factor analysis. It's going to give you loadings, and it's going to give you thresholds. Why it gives you thresholds, I don't know, because everyone hates thresholds, including me. But I want you to know what they are so that you're not confused and don't misinterpret them as difficulties. They are related to difficulties, but they're not the same. You can get from one to the other like this. So discrimination is A times theta minus B, which is difficulty. That's the IRT version. You can rearrange that into what looks like factor analysis, where the threshold is -A times B, and the loading is A. So then to convert from B to a threshold is right here, and to convert A to a loading is right here. If you are using a identification where theta variance is 1 and theta mean is 0, those terms drop, and it simplifies considerably. So A is the same thing as a factor loading, is the same thing as a slope, is the same thing as a discrimination. They're all the same. It's B that switches its interpretation. So you know what an intercept is, right? Tell me what an intercept is. Louder. Expected outcome when X is 0. So in this context, the expected outcome is a logit or a probit when X, which is theta, is 0, right? That's an intercept. Do you remember the cool thing about logits is that they were symmetric? So if I have a logit of, let me go back, actually, come back in the slides here, because that's at the very beginning. They are right here. So if I have a predicted probability of a 1 of 2.2, or a logit of 2.2 corresponds to that, then my predicted probability of a 0 is 10% and a logit of -2.2. Do you remember that? So when you think about an intercept, It's this one here. It's the 2.2. The intercept is the expected logit for the probability of a 1. A threshold is the expected logit for the probability of a 0 instead. So -1 times threshold gets us back to intercept. I have a picture that may help. Oh no, it's darn. I don't want to move that picture. I'm not trying to do that. I kept drawing this on the board so often that I finally made a picture. So here's all of them on one page. So this is an item that has an A value of 4.328. So I took this from, I think, from our example. So that is the slope at its B value, which in this case is -0.376. So right here. Okay? So B, difficulty, location, is the trait level at which you have a 50-50 probability. So when you talk about A's and B's, the reference point for what a 0 means is a logit of 0 corresponds to 50-50 probability. So B is anchored at where logit 0 happens. In contrast, the threshold, or excuse me, let's go intercept. The intercept for the model that goes with B is 1.6. The intercept is not relative to when the logit is 0. It's relative to when theta is 0. You can get from one to the other. So the intercept gives you the theta, expected logit when theta is 0. The B value gives you the expected theta when logit is 0. I need more caffeine. Let me say that again, make sure we get it right. A and loading are the same. That's the easy one. Slope is slope. B is the expected theta when logit is 0. That's 50-50. Intercept is the expected logit when theta is 0. And just because of job security, to turn this thing around so that it's in the same direction as B, instead of giving you the intercept, in some models, it gives you this thing, which is a threshold. It's the intercept times -1. So the intercept is the expected logit of a 1 when theta is 0. A threshold is the expected logit of a 0 when theta is 0. Why they do this to you? 2 words, job security, especially in this field. Psychometricians get more money than I do straight out of grad school. Testing pays. You have to sit in a cubicle all day and probably not wear shorts, but testing pays. So if you can learn this stuff, there is job security in it, in academia or in industry. So depending on your software, sometimes you will get loadings and intercepts. Sometimes you will get loadings and thresholds. Sometimes you will get A's and B's. Sometimes you'll get more than one of those. You just got to know what you're looking at and then what to do with them. Personally, I find the thresholds and intercepts to be less useful than the B's. So let me show you where those show up in M+. These things that we haven't seen yet. dollar signs, that's the M+ way of representing thresholds. And if that isn't a tongue-in-cheek job security, dollar signs, if you understand this, not a coincidence, I think, that they picked dollar sign for threshold. So there are K-1 thresholds for K response categories, meaning if I have 2 possible answers, there's only one switch between them, one threshold. If I have 3 possible answers, I have 2 thresholds. If I have 4, I have 3. So that's why it's $1. If I had a 3-category outcome, it would be $1 and $2. These are estimated by default. You don't actually have to ask for them. And so that's what shows up then on the first part of your output. These are your loadings. Note that they are exactly the same as your discriminations over here. A is to slope is to loading. Then these are the thresholds. The expected logit of y equals 0 when theta equals 0. That's what those numbers are. Yes, question? Threshold? I read what's up there. It's already written down. Oh, the code, yes. Yes. Yeah, so I am freely estimating all 7 thresholds. They're not constrained to be equal or anything like that. Because this part is the item name, daily instrumental activities, that's what DIA stands for. And threshold 1 is the first threshold of item 1. So it looks at your data, figures out how many categories you have, and therefore how many thresholds you need. And it's the first numerically. So it recategorizes whatever you have into 1, 2, 3, 4, 5, even though it's 0 and 1 in this case. So this is the point. It's the transition between a score of 0 and a score of 1 that the model is referring to. So when we have categorical examples, when there's 4 categories, we'll have 3 thresholds for each. But we're not there yet. But yes, these are estimated by default. You don't actually have to write this line. So note what else is not here that used to be here. So this takes the place of the item intercepts. The intercepts would be inside these brackets without the dollar signs in there. There's one more line of code that I had last time that's not here this time. Do you remember? The thing that went away. Error variance, right? Error variance is gone. Guess what that means? If I can't refer to an item, could I have error covariances? Nope, they're gone too. In the world of full information maximum likelihood, they are not possible. You have to work with factors instead, which I'll show you an example of that next time. So then these are the thresholds. If I decided that I don't want to explain what a threshold is in my paper, how do I turn this into an intercept? Okay, watch carefully. Ready? That's how. All done. It's better. Just make sure you do it for all 7 of them. Ta-da! Intercepts. Everyone knows what an intercept is. Yeah, I hate thresholds. But if you take off the minus sign, it becomes an intercept, which is the expected logit of a 1 instead of a 0. But it's still conditional on when theta is 0. it will give you a standardized solution. Standardized threshold, I have no idea what to do with. But take a look at these standardized factor loadings. Look how high those are. Don't those look impressive? So don't I have a kick-ass test? Look at those standard loadings. Look how high they are. Can I compute omega using unstandardized or standardized for that matter? Nope. Because each of these impressive loadings is only impressive in its own little narrow range. Right here. Yeah, these are great items. They are great for low people. They are not great for anyone else. So you have to resist the urge to pay too much attention to loadings when you're trying to get rid of items, because items that are far apart, extreme values of difficulty, those may have low loadings simply because they're so extreme, but you need them. You need them if you want to measure extreme people. So it's not just about the loading. It's where the loading is most helpful. It has to be a combination of both loading and difficulty. Yeah, here's some more plots that I made. Okay, and then there's that. Okay, so all of this is written down here. Yeah, I think that's all I wanted to say about that. I don't want to do estimation today. And new this year, I finally did it. We're not at the end of it yet, but just in case you're thinking, how in the hell am I ever going to write this up? Here you go, words. So I have a caveat here. This is way more text than you would ever be allowed to put into a results section. This is there to try and explain as thoroughly as possible all of the choices that were made in this handout, because what's going to end up happening is that there's another version of the model in terms of limited information estimation that I'm going to show you next time, and I wanted to have you to have words to explain why both of these things were necessary. All right, questions? How many of you have binary items? None of you. So you're thinking, do I need to know this one? You do, unfortunately, because what's going to happen is that for your Likert scale items or other types of categorical items, they're going to take all of your categories and divide them into what are effectively binary submodels. And so then you're going to have, let's say, if you have 5 options, you're going to end up with 4 B's and 1 slope, where each B is its own binary submodel predicting a 0 versus a 1 as determined by the model. So have you heard of proportional odds models? Yes, or multinomial regression as it's sometimes called. Then your binary submodels would be something like 1 versus 2, 3, 4, 5, 1, 2 versus 3, 4, 5. 1, 2, 3 versus 4, 5, and 1, 2, 3, 4 versus 5. And so in that framework, this versus that becomes the 0 or the 1, and then it's a binary model from the perspective of estimation. So even if you don't have binary data, it's all about the binary. It's all about the logit.
You're saying the software is doing that?
Yep. Yep. It figures out how many categories you need. Now the exception to that, if you have a 5-category item but people only answered 4 of them, how many thresholds or B's do I need then? 3. You'll only get 3. But you have to figure out which one wasn't answered so that you know how to interpret your category thresholds. It won't tell you that directly. Fun times. All right, anything else before we adjourn? All righty, then I will see you next week. Let me know if you have any questions on homework 3. Office hours start now.